All right, welcome to another very entertaining video. This one is going to deal with cardiac cycle. Cardiac cycle is important for a lot of reasons. Um, First and foremost being at any given point, it helps us understand the status of the heart, what valves are open, what valves are closed, where blood is going. Before we dive into that, I think it's important to recognize the principle that drives the cardiac cycle. To highlight that point, I just want to quickly let's draw a tube, and we've got flow occurring in this tube in this direction. But let's put in a couple of valves, and these are going to be one-way doors. We can kind of draw like that, and you can see if the door swings open in this direction, then it's going to open up. However, if the door swings in this direction, it's going to hit against that stopper and it's going to close. With that in mind, I think it's really simple simply to ask this question. What dictates these doors opening and closing? And for the heart, it's important to recognize that these doors aren't regulated by muscles or electrical stimulus or anything like that. They're free to do whatever they want. So, what dictates these doors opening and closing? It is pressure. And so the cardiac cycle is merely a snapshot of all of the different pressure gradients within the heart. Now, I do find that sometimes people don't understand that word very well. So when we think about a gradient, this could be a temperature gradient. In this case, it's a pressure gradient, an electrical gradient as in action potentials. A gradient is just a difference across space. Let's see if we can apply that understanding to this little figure we have up here. We could even label these. Let's say this is going to be the atrium. We're going to talk about the left side of the heart. Of course, for the right side of the heart, it's mostly the same thing. The numbers will be just a little bit different because the pressures aren't as high on the right side of the heart, simply because I don't have to fight against gravity. I'm just pumping to the lungs. The lungs are at the same level as the heart. So I just don't need it to be as high. Other than that, it's the same. So we've got the atrium, we've got the ventricle, and then on the left side of the heart, we have the aorta. And this represents the flow of blood through those chambers. Now, it is important to recognize there is no door to allow blood to enter the atrium. It's just coming in from the pulmonary veins. There's no door to let it in. It just comes from the pulmonary veins and goes right into the atrium. And likewise, the aorta, there's no exit from the aorta. The aorta extends through the aortic arch and then down through the trunk and then just spreads everywhere in the body, right? So there's no door getting out. The question is, at any given time, are these doors that we see open or closed? This first set of doors right here would represent the AV valve. And of course, the second set of doors here would represent the semilunar valve. As we think about the first step, let's maybe just number these. These numbers have no significance, but let's think about blood going from the atrium into the ventricle. The thing that I need you to see from this figure is if blood is flowing from the atrium to the ventricle, then door number one, the AV valve, must be open, right? That seems fair enough. Now, what does that mean? It means that because we're following pressure gradients, the pressure in the atrium has to be higher than the pressure in the ventricle. And so that establishes the gradient that drives this spontaneous flow. Now, the atrium in and of itself is a small chamber. It's not really thick. It doesn't have the capacity for a lot of pressure. It might get up to 7, 8 at the highest. But let's say for right now, the pressure in the atrium is like 5. And we're measuring this in millimeters of mercury. Well, because we're talking about fluid flowing from the atrium into the ventricle, we know for a fact that the ventricular pressure has to be less than 5. Of course, this helps us understand that second door, the pulmonary, the aortic semilunar valve, because when we think about the aorta, the range that it can have, and maybe we can write ranges down here. The aorta at the lowest is probably going to be right around 95, maybe up to 120 on an average person, right? With blood pressure 120/80. That pressure is going to be somewhere in that range. So at a minimum, the pressure in the aorta at this time is going to be right around 95. Look at the pressure gradient. This is going to be pushing against that because that's the pressure gradient from high to low. And because of that, we know that this door right here is going to be shut at this given snapshot. So when blood is flowing from the atrium to the ventricle, we know that the aortic semilunar valve is going to be closed and the ventricle will be filling. Now, what happens when the ventricle actually starts to contract? Well, during ventricular contraction, the ventricle, this could be, we could see, let's give this a range, maybe from 2 to 3 up to, of course, the 120 that generates all that pressure in the aorta. We'll see in a second. Let's say it starts to contract, and now the pressure in here is sitting at maybe 60. Well, what's the status of the doors? We see that is going to be pushing against that because it's a lot higher than what the atrium is. That's going to close that door. But it's not high enough to open up the door into the aorta yet. And so we see a scenario as the ventricle contracts where both doors are closed. This, when we see both doors closed, is what we call isometric or isovolumetric. Because both doors are closed, the volume of blood inside the ventricle remains constant. So I think that's enough of a background now to help us understand what the cardiac cycle is all about. All right, so let's graph out the cardiac cycle. And the idea is, look, I can look at a graph and I can kind of see what's going on. This much I will tell you. If you understand the cardiac cycle, then you'll just be able to draw it out like this. Follow me through the process, understand how it works, draw it out, and you'll have a really good sense of what's going on. We're going to draw 3 different lines. Let's start with the atrium, and we'll do that in blue. Of course, as we think about pressure, it's important to recognize what affects pressure. Let's come back up here and add to our list. There are really 2 things that affect pressure. And to illustrate this, I want you to think about a water balloon. Okay? You put the water balloon on the hose and you turn on the water and it starts to fill with water. So what do we see? We see that as we increase volume, this is all about hydrostatic pressure. That increased blood volume leads to an increase in pressure within that balloon. That makes sense, right? The more water I put in, the bigger it gets. Eventually, it can't hold that pressure. It's going to pop. There's too much pressure on the inside, right? So understanding blood volume, this is a direct correlation between volume and pressure. The other relationship is actually inverse. As I increase capacity, I decrease pressure. Now, what do I mean by capacity? Well, what if I just had a bigger balloon, right? If I have a small balloon and I add 1 cup of water, it's going to be pretty high pressure. But if I take that same amount of water and add it to a really, really big balloon, there's not going to be hardly any pressure increase at all because the capacity of the balloon is a lot higher. It can hold more. So we see how changes in the overall capacity of the chamber are inversely correlated with pressure. Let's apply this to the atrium. Like we said, there's no door on the back end to let blood into the atrium. It's coming in directly from the pulmonary veins. So as blood comes into the atrium, what's happening? Volume is increasing. And because volume is increasing, pressure is increasing. So we're going to see a gradual increase over time in that pressure. Now, most of this increase is fairly limited to the fact that as blood comes into the atrium, it typically goes right into the ventricle because 2/3 of the ventricular filling is passive. And we'll talk more about that in a second. But eventually we get to a spot up here where the passive filling of the ventricle can't proceed simply because there's no pressure gradient between the ventricle and the atrium. At this point, the atrium needs to contract. And remember, this is the first part. If we look at an EKG, this is the first part of a contraction, is when the SA node fires, that begins atrial contraction. Of course, now it's not the blood volume that's changing, but it's the capacity of the chamber. So as the atrium gets smaller because it's contracting, that builds pressure. And then as it relaxes, not only has it lost blood because it's pushed that blood with the contraction into the ventricle, but the chamber itself is getting bigger. And so these two things combine to decrease the pressure in the atrium. Let's now take that and let's overlay that on top of what's going on in the ventricle. Remember, if we're filling, that means the pressure in the ventricle has to be less than the pressure in the atrium. So we're going to start that line down here. Of course, as blood comes into it, its pressure goes up, it goes up, it goes up, and then it kind of gets to a point where not a whole lot is changing, right? But right here, because the atrium is contracting, the pressure inside the atrium goes up. That's able to push more blood into the ventricle, and therefore the pressure in the ventricle increases as well. So we see this rapid increase in ventricular pressure. But then as the volume in the atrium goes down and it starts to lose pressure, the gradient flips. And we can see that change in gradient as lines cross. Whenever a line crosses, that tells me that the pressure gradient has flipped directions. And that's always going to lead to either a door opening or a door closing. In this case, what happened? Well, blood was going into the ventricle, but now the blood in the ventricle turned around and tried to go back into the atrium because the pressure gradient flipped. Of course, the one-way door isn't going to let it do that. That's what slams the door closed. We just generated our first heart sound because when valves close, we can hear that thump. Well, now what? Now I've got all this blood sitting in the ventricle. Now it's time for the ventricle to contract, right? We slowed down the electrical stimulation through the AV node, but now we've hit the bundle of His, we've gone down the bundle branches, now we're going to start to contract the ventricle. Recognize, the door is closed, but because of muscular contraction, the capacity of the chamber is decreasing, and that leads to a significant rise in pressure. So we follow this ventricular pressure, it's going to skyrocket. How high is it going to have to go up? Well, if we go back up and we look at the figure that we drew just a minute ago, we recognize that it's not going to be able to open up the semilunar valve into the aorta until it exceeds aortic pressure. So if we look at aortic pressure has been steadily falling little by little as it's lost its pressure. But right there, right where it crosses, that's where we flip the pressure gradient. That, in this case, shows us that the pressure is higher in the ventricle than the aorta, and now we know that the aortic semilunar valve is open. Of course, that's going to lead to an increase in blood volume moving into the aorta, and so we're going to see aortic pressure start to go up. This white is aortic pressure. Let's follow the green again. Of course, this is ventricular pressure. As soon as the ventricle starts losing blood as it ejects it into the aorta, the pressure inside the ventricle is going to start to go down. Of course, pretty soon the ventricle is going to start to relax. So now not only has it lost its blood, but it's also increasing in chamber capacity, and that's going to lead to a rapid decrease in pressure. Now the aorta was feeling all that blood, right? It's filling, it's still there, it's high. But then what do we see? We see right there another change in the gradient, because as soon as the pressure inside the ventricle starts to drop and becomes lower than the pressure in the aorta, the backflow from the aorta closes the semilunar valve. Interestingly, we see and we can record what's called a dicrotic notch. We see a kick up in the aortic pressure right there before it starts its long journey back down. So we call this little kick up right there the dicrotic notch. Now, to help understand that, let's take just a second and imagine a rubber band. Okay, let's take a cross section of that rubber band. Looks like this, maybe a rubber band around your wrist. Well, it's very elastic, right? And indeed, the aorta is made up of a lot of elastic fibers. It's what we call an elastic artery. As the pressure comes in, it expands this so that now the diameter looks like this. Just imagine stretching a rubber band out. All of that pressure has extended that, but recognize that there's a lot of potential energy stored up in the elasticity. When I let go of the rubber band, what does it do? It immediately returns back to its original shape. In many ways, this is just like a muscular contraction, except it's not driven by muscle. It's driven by potential energy stored in the elastic fibers of the connective tissue. But regardless, it's a contraction of the aorta. And as the aorta contracts back down to its normal size, it pushes blood. The relationship between chamber capacity and pressure, right? As the chamber capacity gets smaller, pressure increases, and we measure that transient pressure as the dicrotic notch. Well, now we can kind of come full circle, because we know, coming back to the atrium, that it's always got blood coming into it, and so it's going to start to fill again, little by little. As blood comes in, volume goes up. The ventricle lost all of its pressure, but as its pressure dips below what the pressure is in the atrium, now we open a door, and we start to fill, once again, the ventricle. So let's continue for one more round. Atrial contraction. It's going to come back. And now we can see the process begin to repeat itself. Now, let's identify the 4 different places where we have doors opening and closing. This is wherever we see lines crossing, right? There's one there, one there, one there, and one there. We can label these 1, 2, 3, and 4. What's happening in these regions? Number 1, the AV valve closes. This is my first heart sound. Number 2, as ventricular pressure exceeds aortic pressure, it pushes the semilunar valve open. At number 3, we reverse that gradient, and now the aortic pressure is higher than the ventricular pressure. So at number 3, the semilunar valve closes. This represents my second heart sound. Remember, I can hear when a door closes. It slams closed. And then this last one, number 4, my AV valve opens. Of course, this is followed by the third heart sound because, and we'll talk about this in just a second, as this blood rapidly flows now passively, but rapidly into the ventricle, because this door opens, we hear this swoosh. It's not the most obvious sound. Some people you can't hear it at all, but this will be the third heart sound. It's not the door opening and closing. It's the sound of the blood going through rapidly through that open door. The other two sounds are generated when doors close. All right, one thing that I want to do is overlay on top of this volume. Let's look at ventricular volume for just a second. We can, if we kind of measure these gaps between doors opening and closing, we mentioned earlier that right here, from here to here, both doors are closed, right? This is isovolumetric. And of course, this is isovolumetric contraction. If we do the same thing over here, from when this door closes to when this door, the AV valve, opens, this gap right here is also isovolumetric, but this will be isovolumetric relaxation. What do we know? We know that it's isovolumetric, iso the same volume, because both doors are closed. The amount of blood isn't changing. So let's start right here, understanding volume. We would expect the volume inside the ventricle to be highest during the isovolumetric contraction, right? I just loaded it from atrial contraction. As soon as that door opens, we get ejection, fairly rapid, and that's going to come out and it's going to stop right there because, again, right here we're isovolumetric, so that's going to be a straight line. As soon as that AV valve opens, we get a quick flow, but it starts to taper off because all we're doing is dealing with pressure gradients, right? And we get about 2/3 of this inflow, and it's all passive. But then what do we have? We have atrial contraction right here, right? And so we get our last bump, and this is 1/3, and this is active filling, and then we're isovolumetric again because that door closes. So that shows us the pattern of volume. We could put some numbers to this, talking about milliliters maximum and normal. We're talking about 120 milliliters minimum, right? I don't want you to think that the ventricle's fully empty. It's not. It bottoms out at about 50 milliliters. This difference right there, 120 minus 50, 70 milliliters, then represents the stroke volume. This is how much volume is ejected from the ventricle into the aorta with any given contraction. Now that we've drawn that out, I hope you can kind of see what's going on. We can further subdivide these into, for example, ventricular diastole. Diastole is going to start as soon as we're fully relaxed and go through all the way to contraction. We can break this gap down into diastasis and atrial contraction. We can look at some other things. The most important thing is to really understand what's going on with pressure. And then as long as we understand that there are two things that affect pressure, overall volume and chamber capacity, and how we change those two things to alter pressure gradients. These pressure gradients then open or close doors, and as those doors open and close, we follow this pattern that represents one heartbeat.